Welcome back to the deep dive. Today we're tackling something, well, deceptively simple, but incredibly tough for robotics. Getting a grip.
Sophisticated manipulation.
Yeah, it's this massive bottleneck, isn't it? You see these amazing humanoid robots, like Atlas from Boston Dynamics, doing flips, balancing. They've pretty much nailed locomotion, even vision, to a large extent.
Right.
But then you ask them to do something trivial for a human, like, I don't know, pick up a key they dropped, or maybe turn a specific kind of wrench.
And all just stops.
Exactly. The whole system just grinds to a halt.
And that's the core of it today, isn't it? What Elon Musk calls the hands problem. Our mission here is to give you that quick, structured insight into why the most advanced robots are, well, fumbling with this potentially $5 trillion opportunity.
And that number, $5 trillion by 2050 for humanoids, it sounds huge, but analysts genuinely see that potential market size.
But yeah, these hand limitations, they're consistently cited as the biggest single roadblock to getting these robots out there doing general purpose stuff, in factories, maybe even homes. The stakes are just massive.
Okay, so let's dig in. Where does the difficulty start, I guess? The human hand itself.
It really is an evolutionary marvel. I mean, roboticists, they actually call trying to copy it a kinematic nightmare.
A nightmare? Okay, why?
Well, just look at the structure. You've got 27 bones in your hand, and that translates to roughly 25 to 27 functional degrees of freedom.
Okay, hold on. Degrees of freedom. DOF. Let's quickly unpack that for listeners. What does that actually mean here?
Right, so DOF is basically the number of independent ways something like a joint or a whole system of joints can move. Think of it all the ways your finger joints can bend or your wrist can twist and turn.
Got it.
And having over 24 of those in the hand, that's what lets us do everything from, really powerful crushing grip to incredibly delicate adjustments of something within our hand. We call that in-hand manipulation.
Right, like fiddling with a coin or a pen without putting it down.
Exactly that. And trying to replicate that mechanically. Well, that's where the trouble starts. Let's look at Tesla's Optimus, because they're really going for that full, human-like, anthropomorphic design.
Yeah, they seem all in on mimicry.
They are. Their first version, the Gen 1 hand, it had 11 degrees of freedom driven by 6 actuators. It sounds like a lot, right?
It does.
But even then, it was missing some really basic human hand movements, like spreading your fingers apart side to side, that abduction-adduction. It just couldn't do it.
But they iterate incredibly fast. The new Gen 3 hand, that's aiming for, 22 DOFAT?
22, yeah. That's getting incredibly close to human-level complexity. And the way they're doing it is interesting, too. This tendon-driven system.
Like our own forearms, basically.
Pretty much, yeah. The actual motors, these tiny servos and ball screw actuators, they're not in the hand itself. They're moved back into the forearm, and they pull on tendons that control the fingers.
Why do that? Is it just about saving weight in the hand? Or does it help with other problems like heat?
It's really both. It's a clever bit of design, actually. Pulling the heavier motors out of the hand makes the hand itself much lighter, lower inertia.
So it can move faster, react quicker?
Exactly. And it helps manage the heat. You keep the heat-generating motors away from the more delicate parts, the sensors and joints, in the hand itself.
I saw something about a clutch in that Gen 3 hand design as well. A mechanical clutch?
Ah, yes, that's a really neat engineering detail. It's on the flexor dry, the part that closes the grip, and it makes the joint non-backdrivable.
Non-backdrivable. Okay, what's the payoff there? Functionally, what does that do? Is it like putting the brakes on?
That's a perfect analogy. It means once the robot grips something heavy, that clutch engages and locks the joint. The motors can then essentially switch off for that joint.
So it can just hold something heavy?
For ages, potentially, with zero power being consumed by those hand motors. For a battery-powered robot that needs to work all day, that's a massive efficiency gain.
Huge. But that level of complexity, did it bite them back when they tried to scale up the earlier complex hands?
Oh, absolutely. They hit a major wall. Reports suggested those early hands were something like 25% of the entire robot's cost.
A quarter of the cost, just for the hands.
Yeah, and maybe 50% of the whole engineering headache.
Yeah.
That complexity led straight to problems like motors overheating, reliability issues. It just wasn't ready for mass production. It really highlights this tension, perfect human mimicry versus something that actually works reliably on a factory floor.
And that tension really explains the different paths other big players are taking, doesn't it? It feels almost like a philosophical split.
It really does. Look at Boston Dynamics with Atlas. Their approach is totally different.
Simple grippers, basically. Claws.
Right. Simple 2 or 3 finger claws. Atlas gives up almost all that fine dexterity. Why? Because its focus is on raw power and being tough.
Because it's hydraulic, right? So it's built for force.
Exactly. It needs to be durable enough to throw a heavy tool bag or, survive a fall. It's designed for high impact, high force. Dexterity isn't the main goal there.
And then the third way, Agility Robotics Digit. They seem even more focused on just getting the job done.
Digit is probably the most pragmatic example. It uses a really simple two-finger setup, basically parallel jaws, like a basic claw.
Because its job is specific, warehouse boxes.
Exactly. Their focus is pure simplicity and bulletproof reliability for moving boxes and totes in a warehouse. That's it. Their design choice says a lot. For many industrial jobs, you probably don't need 27OF. You need something that just works every single time.
Okay, so we've got these different mechanical approaches, super complex, super simple, somewhere in between. But even the best mechanics are missing something fundamental the human hand has, right? The sense of feel. Is that the real blocker?
I think it's arguably the bigger challenge right now, yes. The sensory gap is just enormous. Think about human touch. We have thousands upon thousands of receptors packed into our skin, different kinds for pressure, vibration, temperature, even pain, which is actually useful feedback.
Right. Tells you not to grip the hot thing.
Precisely. And all that data feeds into our sense of proprioception, just knowing where our hand is without looking, and lets us adjust our grip strength dynamically, instantly, intuitively.
And robots, they just don't have that rich stream of data.
Not even close. Current tactile sensors for robots are still, well, pretty basic. They can be bulky, fragile, and honestly, the field just doesn't have the kind of standard, widely accepted sensing solutions that we have for, say, vision.
So it's not just the sensors themselves, but using the data.
That's a key finding, actually. A big review of research papers pointed out that the real bottleneck is often the integration. How do you take data from maybe multiple sensor types, touch, force, temperature, and feed it into the robot's control system in a way that's actually useful in real time? Many projects end up using just one simple sensor type or sometimes none at all, relying purely on vision.
Is anyone making real progress there? Is Optimus managing to integrate touch?
They're definitely pushing on it. The latest Optimus hand reportedly has much more tactile sensing across the fingers and palm. And they showed that demo.
Ah, the egg demo.
Right. Gently picking up and holding a raw egg without crushing it.
That requires incredible force control.
It implies really fine force regulation, yeah. Probably less than 1 Newton of pressure difference. Yeah. So it shows their control systems are starting to effectively use that tactile feedback, at least in controlled situations.
But making that kind of sensitive electronic skin robust and cheap enough for millions of robots, that sounds like a huge manufacturing hurdle.
It absolutely is. The current technologies, things like capacitive sensors, piezoresistive, optical, even magnetic ones, they all tend to struggle with trade-offs. It's hard to get high sensitivity and robustness and integrate multiple feedback types like touch, heat, shear forces without making it super expensive or really bulky. How do you make something tough enough for a factory, but sensitive enough to, say, feel texture? It's really hard.
Okay, so if the mechanics are hard and expensive, and the sensing is arguably even harder and more expensive, it brings us back to a fundamental question. Does a robot hand actually need 5 fingers?
Yeah, and the data, especially from industry and competitions, increasingly suggests often no.
Really?
Look at things like the Amazon picking challenge, where robots have to grab all sorts of different items. The winners often weren't the most complex hands. Many use simple suction cups or basic parallel grippers. They prioritize reliability and speed over trying to mimic a human hand perfectly.
I've heard 3 fingers often mentioned as a good compromise, though.
That's a common idea, yeah. 3 fingers seem to hit a sweet spot between offering more dexterity than 2, but being much simpler than 5. There's a well-known research hand, the Barrett hand.
Right.
It's got 3 fingers, and it's been shown doing things like operating a power drill quite effectively. And interestingly, studies of human grasping suggest that even when we use our whole hand, most of the actual work, the functional force, is often applied by only 3 fingers anyway.
Only 3.
Huh. Yeah. And get this. Research has even shown that simple 2-finger grippers can do surprisingly complex manipulation, controlling an object in 3 degrees of freedom.
How?
By being clever. By using the environment. They might push the object against the side of a bin or slide it along a table surface, essentially using that surface as a temporary 3rd finger to help reorient the object.
Ah, so you're offloading the complexity from the hardware into the software, into the AI controlling the movements.
Exactly. Solve it with smarts, not just more joints. But we do have to be careful. There are tasks where more fingers clearly help.
Like what?
Really complex parallel tasks, trying to grasp multiple small objects at once, maybe. Or something like tying a knot that typically requires 2 hands, or, well, interestingly,
Go on.
studies involving people with polydactyly, meaning they naturally have 6 fingers.
Whoa!
Yeah, some individuals with 6 functional fingers have demonstrated they can do tasks like tying shoelaces using just 1 hand, which suggests our standard 5-finger setup might actually be a limitation for certain highly complex parallel manipulation tasks.
So maybe 5 isn't even the optimal number for dexterity in some cases.
It might not be. And that opens the door to research into non-anthropomorphic designs, hands that don't look human at all.
What kind of designs?
Well, there's some fascinating work showing that a hand with, say, 2 opposing pairs of 4 fingers, so 8 fingers in total, arranged differently.
Okay, that sounds wild.
It looks different, for sure. But that configuration has been shown, theoretically and in simulation, to be able to control an object with 6 degrees of freedom during in-hand manipulation. That could potentially offer more dexterity than our human hand, which is limited by having only 1 thumb opposing the other fingers.
So pulling all this together, sounds like maybe roboticists got fixated on copying the number of fingers, the 5, instead of focusing on what really makes the human hand so good.
That's a strong possibility. That's the core of the debate, really. Did we take a detour chasing perfect mimicry? Because right now, the overall complexity, combining the mechanics and the sensors, it just doesn't match human capability yet. But maybe the human hand's biggest advantage isn't its sheer number of joints. Maybe it's its robustness.
You mean the fact that it's squishy?
Exactly. It's soft, it's deformable, it's flexible. That allows us to be a bit imprecise, to adapt if things aren't perfectly aligned. We can manage uncertainty in the real world because our hardware is forgiving. Robots with rigid, complex hands struggle with that messiness.
Okay, so let's recap this deep dive. The hands problem, holding back this humanoid revolution, it's not just about building tiny robotic joints. It's this incredibly complex interplay between mechanics, rich sensory feedback, especially touch, and the really sophisticated AI control needed to make sense of it all, something our bodies just do.
Which leaves us with a really interesting question for you, the listener, to think about. As this field develops, if it keeps turning out that simple 2- or 3-fingered grippers are good enough for most jobs,
Right.
and if non-human-looking designs, like maybe those 8-fingered hands, actually prove more dexterous for really complex tasks,
Yeah.
should the field maybe give up on strict human mimicry?
Just abandon the 5-finger goal.
Potentially. Should the focus shift entirely to designing hands that maximize utility, robustness, reliability, even if they look completely alien? Is that the path to unlocking that $5 trillion potential rather than perfectly copying ourselves? It's a huge design question with massive implications.